Good morning, and welcome to N-Simplex Pachinko. This is Obi-Wan Pez. We're going to be doing a Friday math stream to make up for the fact that I wasn't here on Wednesday night. It was my spouse's birthday celebrations, so decided to take care of that instead of streaming. I know, how dare. Negative Plasma, Benji Boy. Good morning. Alright, and this is going to be in addition to my Friday night stream, which is going to be more Valheim, I'm sure. So if anybody's into that, we'll see you then, but... For now, let's talk about some math stuff. So, I did have one person who was interested in talking about gradient descent neural networks. I can do an overview. It's not going to be like a super great. Of course, I can also wait until that person is actually here, but Yep, so my Friday night streams are game oriented, and like I said, it'll be like most likely, like I said, Valheim tonight. That's not what I wanted. Where's all my master stuff? There we go. All right. Neural networks. Used to have hiding somewhere in here. Let's see if this works. This is a seriously old program. Runs off of Scilab, not even... It is a free clone of MATLAB. Do we have the thing? Rungekutta. Okay, here we go. Let's see. So... Absolutely, go for it. The good news about this program is I commented it well. There we go. Nice. Alright, so something's on sale. Alright, I'm gonna be a jerk here. You purchase an item, it is 43% off. And you paid $31.50 for it. This is probably going to have really nasty implications, but whatever, it's cool. Alright, so if you take the original purchase price and then you have your D is going to be discount. Oh. They decided to give me an actual eraser this time. Alright, discount as a decimal. And sale. I know, right? Bertram, nice to see you. Yep, I decided to try this up. Whatever, try this out. So that I've been trying to do like a Monday math morning sort of thing, but you know, because I like alliteration. But this week I got busy doing other stuff, and then I was like, I don't really feel like it. And then Wednesday we were celebrating my wife's birthday, so I wanted to, like, you know, not be in this room for 3 of her waking hours. Hey, Baka Awful. Welcome in. So over the summer, it's going to be a lot more loose in terms of like what times I'm going to be streaming and when and how many times per week and things like that. It's probably still only going to be like 2 math and 1 gaming, and most likely I'll keep my standard times of Wednesday and Friday nights. I just want to try to get like a Monday, Tuesday morning stream in there too, so that people are, you know, actually able to come in, for instance. I am not teaching this summer, generally. I am doing a day camp the week of the 27th, whatever that is. Yeah, 27th. So the week of the 27th, I'm doing a day camp. I'm not going to be here like the entire daytime. So that's going to be out. And then the week of the 4th, I'm just not going to be in town at all. So we are going to go see family and stuff like that. So that the 6th and the 8th are my usual stream days. I'm not going to be here for that. I'll put that on my calendar, wherever that is, on Twitch. Make sure that it's clear. And then apart from that, I've pretty much got like all summer. And my kids are going to like camps a lot randomly. And when they're home, I'm probably not going to be streaming during the mornings. Because, you know, kids. Probably should pay attention to them for some reason. Alright, so, Benji, let's see. So if we have our P original purchase price and our D discount as a decimal, not as a percentage, and then S is going to be our sale price, we can rewrite all of this as our price. Wow. Our price multiplied by our discount is going to be equal to our sale. Now, notice that this is not exactly... Oh, you know what? No. Whoops. That's not quite true. Oi. I forgot something important here. I know what I meant. Okay. So P is going to be multiplied by the like percentage that we have remaining. So if it's 50% off, that's easy. It's 50% of the price is now remaining. If it's, in this case, 43% off, because I'm being a pain, it's not going to be 43 or 0.43. We need to take this and say, okay, if it's 43% off, what's left? How much of the price is left? So we can take this and say, okay, this is going to be 1 minus whatever our discount is. So in this particular case, we end up with a 1 minus a 0.43, which is a 0.57. All right, and that's equal to the sale price. Now, I know what I was thinking. P times our D is going to be equal to the amount that's discounted. Man, this is just crazy. Okay. Right, and instead of doing this way, we could also instead do that 1 minus calculation at the end, where we'd say, okay, well, if this is the amount discounted, then we say it's P minus A is going to get us our sale price. But, you know, however you want to arrange this, this is all good. So our original price is, we don't know, right? Yep. Yep. So we're going to take our sale price, which we do know is $31.50. And then here, like you said, divide both sides by 0.57. That gets us our P, the amount that's left here. Where is my calculator? Alright, so then here we get our original price is going to be off the screen. That's fine. There we go. Original price is going to be 55.26. Alright, what else y'all got? Hey, Nerdist. How are you? Welcome to the channel. Welcome back in, I suppose. And thank you for the follow. Pen Center. I don't think I know that one. Ooh, very nice. Also a math streamer. Oh, that's really cool. Well, I will have to give him a follow here and check out his stream later on. Next stream will be Thursday, September 1st. Oh no. I hope not. Well, it's perfectly possible. Anyway. Okay. Well, basically, I do a lot of just kind of homework help. Let's see what anybody wants. And I was also going to probably do a little bit on neural network gradient descent. I can't guarantee that it's 100% accurate because it's been 10 years. 12 years. But I do have some experience with creating neural networks, and I just want to kind of give an overview for somebody who is asking about like one of the people from another stream was like, oh, well, do you know statistics? Because I'm trying to do this. And I was like, yeah, you probably want a neural network. And he was like, I am going to stop over. So. The very basic overview of how this neural network works. Not necessarily like going into super specifics or anything like that, but you know. This does involve a little tiny bit of matrix theory for anybody who has done matrices or has no idea how they work. I will give you a brief overview of how matrices work and how they apply to neural networks. Anyway, so if anybody else does have any questions, feel free to drop them in chat, and I will get to it either after I do this or in the middle if this is taking particularly long. So we'll see how it goes. So a neural network basically is just getting a computer to start thinking sort of in the same way that a human brain might sort of do calculations. It doesn't literally do 100% the same sort of thing, but, you know, it's close enough that people are like, hey, this is kind of analogous. And a lot of brain researchers and neural network researchers have gotten together and been like, yeah, you know, it's sort of similar. It is at least analogous. So in a neural network, what we've got is a series of inputs. And then somewhere over here, we've got a series of outputs. Now, these outputs and inputs could be connected directly, or they could be connected indirectly through what's called a hidden layer. And I will put a hidden layer in here just because. You know what, let's do a different number. I want all of the numbers of nodes to be different in each of the places. This could be literally anything that you want, or anything that the structure demands. So you have a series of inputs. Maybe this is like a matrix for this could be, for instance, a set of pixels on a screen, and you want to do like handwriting recognition or something like that. So one of the things that we used to do was say, if you wanted to have this as like a block of pixels, this would be, there's only 5 of them, that's not really interesting, so 6. So this is 6 pixels, which are arranged like this. Yeah, that's 6. Okay. And they're totally squares, so don't let anyone tell you otherwise. There we go. At least somewhat equal rectangles. So basically we label these pixels like 1, 2, 2, 3. Man. I'm not liking the online version of this whiteboard. 5 and 6. Friends of the channel will know that we had some problems with the whiteboard app. And if you were there for any of that, I do apologize profusely. And then we go down and label. These are our inputs. 1, 2, 3. Come on. 4, 5, and 6. So these correspond with these things. And if we want to do, again, some sort of handwriting recognition, we can go through this and say, like, each of the pixels are going to contain some sort of, it's not just going to be on or off. It's going to be like, within this region, and I guess technically, then it's not a pixel, it's like a block. So literally we could use these blocks here. So if I wanted to fill like this 2x3 area in here with some sort of shape. So I want to write a number, for example, something like this. And I want to recognize what number has been written in the block. Then what this does is we take each of these sections of the block, count them up, and call those our inputs. Those inputs then get tied to this hidden layer. And I'm going to regret having done all of these, but whatever, it's cool. I'm doing this for you. Okay, and like I said, literally all of these get tied into all of the hidden layer here. The hidden layer, we don't actually necessarily have any clue what it's going to do. In reality, it's probably got something to do with, let's break this down into like what pieces do we know exist for these particular numbers. So, right, if this is going to be like the output will be a digit. So we need to then have 9, or well, 10, 2, 3, 4, 5, whoa, 6, 7, 8, 9, 10. Oh, do I have the option now of making it a different? Yes, nice. So you can do either partial or entire stroke. That's cool. Okay, I've been wanting them to do that for a while now. Alright, so all of these are connected to all of these. Likewise, all of these are going to connect to all of these. So, again, this would take a while. Oh, I forgot my glove. I wonder why my hands were sticking so much. Alright, there we go. Alright, so. So all of these over here are connected to all of these over here, and all of these over here are connected to all of these over here. So first layer connected to second layer connected to third layer. We could have multiple hidden layers So not just one in between. There could be like 2, 3, 5, 100 different inner layers that we have no idea what they necessarily do. In terms of handwriting, what we'd probably have is that each of the hidden nodes on the inside would detect a certain kind of shape. So for instance, this one here might be like something that goes like this. This one over here might have something that goes like this. This one might be this way. This one might be this way. This one might be a vertical line. This one might be a horizontal line. And then we'd probably have more other stuff. So like there might be intersections, or we'd have like diagonal, right? That'd be the other obvious one. And actually, we wouldn't get intersections for this, because that would be a second hidden layer if there's going to be any. All this does is it says, okay, based on the input that we got from this thing up there, you know, how similar are each of these things to what's in each of the blocks? So in this case, we've got something that's like a vertical line-ish that's in blocks 3 and 4, sort of. It's more similar to the vertical line one than it is to any of the rest of the stuff. So it might have a little bit higher of a weight on these, vertical line connection for blocks 3 and 4 than any of the other shapes. So, hidden layer. Alright, and then the one here in 6 would be most likely similar to a horizontal line. 5 would be rather interesting because it has a vertical part and also something that goes to the left. So most likely it would be most similar to this one here. Despite the fact that it's curved, it looks more like this than it does like just a flat line of either of those kinds. Up here again, we've got like mostly a vertical line. This one here is sort of like diagonal, so it'd be more weighted toward those. So what we would do is we would sort of randomize the weights that are going between all of these. So each of our weights with subscripts I and j give us a unique location inside of a matrix. So W matrix is going to be our weight matrix. The inputs are typically listed as like x, or x sub I is going to get us like the individual terms in that particular matrix. This is going to be a vector, so it is a single column or a single row, depending on how you feel like it, with however many of the opposite thing, so rows or columns, that are here. So in this case, again, term 1, term 2, term 3, term 4, term 5, term 6. Just how we're going to do it. Now, if you wanted to go the other way and do 1, 2, 3, 4, 5, 6, or like 1, 2, 3, 4, 5, 6, you could do any of that because this is going to take care of that. As long as you're consistent and not like using this on a new, like different system, as long as you're consistent, then it's fine. You're going to have to train it on a new set of data every time that you change it. I mean, could be your old data too, but... So what we're going to do is we're going to say that our x sub I is going to be multiplied by W ij And this gets us our like hidden layer. So this is going to be H sub j. Okay, and then when we do, after we do that, this is also going to take H sub j as our new inputs for the next layer over for this calculation here to figure out what we're going to get for an output. So then here we would get H sub... Alright, might as well. Just cut it off, it's fine. Okay, and then the next section is going to be H sub j times our new weight matrix, which connects j to k, which is then going to get us our outputs, or usually y sub k. I'll use capital letters to represent the inputs and outputs, and H's are just going to be all of our hidden layers. If we have multiple hidden layers, a lot of times we'll put like a 1 or a 2 or a 3 to denote which hidden layer it is. But this is the basic overview, like I said. Okay, so like I said, all of these are also all connected to every single one of the output nodes. I just don't want to clog this up too much. That's how VR works. Sorry, Bertram, is that a joke? I mean, it's kind of like you can use stuff like this for VR, but it's not necessarily going to be like really what's happening. You could also there's a lot of stuff you can do with this. Basically, if you see any reason to like try to get a computer to sort things into two different stacks, which are not going to be 100% obvious, like what the answer is. It might be obvious for you because, again, you're a human, you understand, but there are ambiguous cases. So, for instance, if you had a block, right, you have a block like this, and somebody writes this number, right? Anybody in Europe knows what that number is. Yeah, it's a 1. Typically, again, like I said, in Europe, we see that this is how the number 1 is written. And it's usually, right, this is written because it started out, or sorry, we write this in America. Only a long time ago, somebody was like, this is really confusing because this is too close to a 7. And so they were like, okay, we'll put a bar along the bottom and make it a 1. So that you don't confuse it with a 7. Which, again, in Europe, typically put a cross in the middle to make sure that you understand that this is a 7, not a 1. So it gets kind of confusing for a computer system to do this because it needs very set rules. It needs rules. So what you do is you say, okay, let's have this thing look at the overall picture and then take a guess. So it's going to come in here. It's going to plug in the inputs for these particular numbers. It's going to multiply those inputs by our weights, Wij, which are going to be set at random at the beginning. Or like, you know, they're going to be set to specific values, whatever they are. Usually it's randomized or it's been sort of seeded by a person. It's like a researcher. And then this gets you our hidden value. Our hidden value times our next group of weights is going to then get us our outputs. Our outputs tell us which of the numbers is this thing going to be. So for instance, the output here is going to be like max of y sub k. So whichever one has the highest value, we end up looking at this and saying, okay, well, the output here is going to be 0, 1, 2, 3. Bogdevil, good morning. Yes, so I had a request from one of my other viewers that we look into gradient descent neural networks, and I'm attempting to start the like very basics of it. I haven't done this in, like I said, 12 years or something, but but yeah, this is the idea. So if we have some sort of maximum value inside of our outputs, we pick whatever that is, and then the index of that is going to be the output. Or in this particular case, right, the output is going to be equal to the index of the max of y sub k. So in this case, this is going to spit out a 3. Now, if we're on our like first iteration, this is possible, right? That it's possible that we had this shape right here was our input, and we got a 3 as our output. Clearly, this is not correct. So what our program will do then is it will start feeding back and saying, okay, I have a bunch of training data which tells me what the inputs are and what the correct output is. So this is why you need to do the whole training thing. This is, again, basically, very basically, how the human brain sort of works and learns, is that your neurons start firing. You get input through your various senses. You get an output which tells you how to respond. And then you are corrected. Whether that be through something that is unpleasant, you know, you get more input, which is like, ugh, I didn't like that. Or you are told directly, no, that is incorrect, and you understand what that means. And when you're told, no, that's incorrect, you can then go back and refresh your neurons to say, no, 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 let's fix that. Let's go back and change things. So what happens is we feed this backward, and it looks back at the previous layer of weights and says, these weights are incorrect. Let's change the weights in order that our outputs will more correctly reflect what we got for our training. So what I have here for this other one was delta J, or delta JK, I guess. It's going to be equal to man, this stuff that I'm looking at is like very specifically tailored to like this particular thing that I'm looking at. Now I can't remember what it all stands for. Let's see. Okay, so this is the, I think these are probabilities. So I said, what is that? That is the ASCII. So I was doing some ASCII code with this, which is why I'm hesitating greatly, because I got to remember what this is actually doing. And I mean, I have this in a book, but it's going to take me a little while to remember. Okay, let's pull out the book, because come on. Yeah, I don't have that command, sorry. Granted, I probably should. Ugh. Alright, that was a little gross. Come on now. And where's this book? Come on, man. Look, I don't want to do this. Why? Stop. Oh my god. It's weird stuff. Anyway. I've been having some weird input issues with my computer the last couple of days. It's just decided that, like, it's gonna, yep. It's just decided that it's gonna, like, start doing its own thing, and, oh. It's in the one that says textbook. Alright. Oops. I don't think that this is up anymore. Yeah, not so much. Yeah. Oh well. And also, I should not do that on my active window. So Bog Devil, yes, I do have a YouTube. It is under nSimplex Pachinko, same as the channel name. Mm-hmm. Gotcha. It is also possible that it was from Twitch. The other option is that I was just on some random channel somewhere and mentioned that I teach math, and they're like, oh my goodness, do you have a thing? And if I said yes and gave them the thing, then alright, so I did like a diff is the absolute value of the output minus ideal. And then, well, that's just going to be weird and confusing. Let's go like that. And then delta JK is going to be equal to also possible. Alright, where is... Ugh. Alright, let's see. That's a lot of partial derivatives. I mean, the good news here is it's not really. Because these are discrete, it's not technically a derivative, and because it's not like a continuous function, we're not using that. Well, I guess we are using a continuous function. One of the other things that we're doing is that within all of the weight areas, what we're doing is we're going to say that we want to take a function and plug our inputs into the function. And that'll determine whether or not we're going to activate. So oftentimes what we do is we use an activation function that is what's called a sigmoid, which is a good option to use. What we'd be looking at here is there we go. So a sigmoid function looks like this. You might know it under the name logistic. But typically, it's going to look something like this. It's going to have a value that goes like that, and then flattens out again. Gets pretty close to the top here. So the logistic function looks like two exponential functions that are kind of tied together in the middle. And this area right here, typically, this is going to be a 1, this is going to be a 0, and our intercept here should be around 0.5. This is like an idealized version. Again, you can like manipulate a function to make it work like this, to make it end up have these particular properties. It's not particularly difficult, and especially if you all know my penchant for yep. You all know my penchant, those of you who have been here a while, for doing function transformations. It's the same deal. Basically, you can get the sigmoid function to have these particular properties no matter what your inputs are. or otherwise you can alter the sigmoid function to make it have alternate properties or alter your various other things. So we're going to get output values that are between 0 and 1 for each of our nodes as we go across, which then says, is this going to be activated? Which are going to be our particular values for the product of like x times w, and then also the h times w. So we always, like I said, we always get values that are either going to be pretty close to 0 or pretty close to 1. And that's going to be what causes the certain neurons to activate, and then that's what ties it into the next layer as we keep going across. And also you can alter your sigmoid function, again, fairly easily to make sure that, like, you know, you're not going to get a value of 0.2 or 0.3 and then have no idea what that means. You know, you're typically what we do is we say, if you're above 0.5, then it's activating. If you're below 0.5, then it's not activating. And if you're like, well, what about 0.48 or 0.49? Because that's really close to activation. Well, if you've chosen your function correctly, if you've chosen your sigmoid correctly, you can actually create a sigmoid function which looks basically like this. Such that a minor difference in the inputs pretty close to, you know, 0 up here are going to basically have like no effect whatsoever. It's going to be pretty much almost definitely not activating or almost definitely activating every single time. So you just have to kind of play around with the function itself and determine what kinds of parameters you want on it. Yeah, this spends so little time anywhere near 0.5, I wouldn't even worry about it. And again, if it ends up that, you know, your outputs are incorrect, then use the backpropagation method and it'll fix it. It'll eventually get values that are probably not that close to 0.5. It'll be pretty close to 0 or pretty close to 1 when you get the outputs. All right. So let me see if my other program in here is any good. Jerks. Come on now. Oh, I see. Why are you like this? Weird program. Okay. I don't understand what the problem is here. All right. Um, sorry. My computer wants me to accept Adobe Acrobat as like the default to open PDFs, and like, of course, yes. But I keep trying to select something, and it's like, oh, you're selecting the Acrobat DC or whatever, so that's not right. I just don't understand. Why? No, I don't want reader. Ugh. What is your problem? I'm just gonna fight with this for the rest of the stream. It's fine. I don't understand. Aha! You're from Britties. Yep, there you go, Bog. That's where I've seen you before. Yep, at some point, I was watching her play Outer Wilds, and then she was like, "Oh, said, yeah, I just randomly said something about math," and she was like, "Oh wow, you stream math," and then that became a thing. Yep. See, I can pretty much always tell what what community somebody's with if they have the. Yep. If they have the emotes for it. What the? Huh. Okay. Yes. Outer Wilds was the very first thing that I streamed on Twitch. I decided that I was going to do a like first walkthrough guide, basically, of the Hmm. All right. So anyway, yeah, I was streaming Outer Wilds as my first thing, and I was doing like walkthrough slash like guided tour, basically, for like, hey, if you are interested in playing Outer Wilds, here are the first few things that you might be interested in seeing. And so I like walked around and showed my viewers, there were no viewers, all of the various things that, you know, you could see on your first playthrough, that kind of thing. Feed forward. Transform, Boolean, eh. Yep, I just started looking around for random people who were playing Outer Wilds, and then Britt came up at one point, and I was like, oh, this is really cool. So, yeah, had a good time with hers, and yeah, so I had originally, I think, watched it with somebody that I was watching for Elite Dangerous and a few other things. Her name is Psyche, and she's a Northern Ireland streamer. Um, and she, she had massive feelings. And like whenever I watch the end, it's like 90% of the time half of chat is in tears, and it's just like, I love this. And then she played the DLC, and like the reveal is just absolutely amazing, both at the beginning and the end for the DLC. It's just such a great game. And yeah, my only regret is that I won't be able to play it for the first time again. Alright. One of the reasons that I was trying to get my spouse to play it is I was like, I think you will, like, there's really good, like, the whole experience is just an experience to be had. Like, I think you should probably play this. And she was like, eh. Okay, homework 4, singular perceptron. Yeah. Just such an amazing game. Alright, so let's see. Y sub j. It's going to be sigmoid. Delta is equal to those things. Okay. Okay. I got it now. So, delta jk is basically going to be the weight probability. Like the probability of y, essentially, times 1 minus the probability of y. Oops. Capital. So this is going to be like pseudocode. I mean, it's not going to be pretty, but all right, multiply by the diff that we had in this previous one. That, yeah, that's great. There we go. Move. There we go. So the output and the ideal here, this is really the, like, probability of y minus the, like, ideal y? What should that be? Oh, yeah, and oh my god. Yeah, you might want to see Psyche's playthrough. It's pretty amazing. Or at least, like, certain bits of it. Commander. So yeah, py minus y ideal is going to be that difference that we have here. That's going to be what we get here for our difference. The actual change in the JK node that you're making is going to be this stuff. So like what you got for your output, the probability for your output, out of the sigmoid function multiplied by 1 minus that. So this is a little bit like binomial theorem almost. And then multiplied by the difference. And then we feed that back and say that the weight JK is going to be the previous weight JK that I am not. Interesting. Is that like people discussing the... Not particularly Outer Wilds, doesn't look like. Oh, there we go. Come on now. Huh. Interesting. That's not really... Alright, whatever. Hey, two curbs. Yep, so that is neural net weight matrix that we're looking for. Yep. Weight matrix that we're trying to like reassign values for. So the next set of weights is going to be equal to W sub JK, the previous set of weights. Again, pseudocode, so it's like reassign these things. It's going to be the previous values plus... there's going to be some eta value, which is like a damping value. So if you notice that your particular neural network is like training too quickly or too slowly or something like that, you can manually alter eta to try to get it to do different kinds of behaviors. All right, multiply by the thing we just did, so that's our delta JK, multiplied by our particular input values. And actually, for JK, that'd be our hidden values. So that'd be H. JK. And actually, that's, sorry, h sub j. So this can get to doing all sorts of fun stuff. So yeah, our new weight value is going to be equal to the previous weight value times eta times the change factor times our input from h that we got from the previous setup. I just don't know. I really like the second movie. Everybody keeps slamming on it, but I really like the, I even like the architect a lot. Like, he has an incredibly inflated sense of ego, but at the same time, it's like, well, that's probably how a computer would actually talk, is like it would search for the ideal language to be using for any particular situation. RELUs, real, I don't know that one. Rectified linear activation, okay, cool. Rectified linear unit. Alright. Okay, interesting. Okay, so sigmoid and hyperbolic tangent activation functions can't be used in networks with many layers due to vanishing gradient problem. Rectified linear activation overcomes the vanishing gradient, allowing models to learn faster and perform better. Okay. And default activation when developing multi-layer perceptron and convolutional neural networks. Cool. Well, thank you. Piecewise linear outputs the input directly if it's positive, otherwise it's 0. Okay. And GELU. Guessing that's gradient, but... Oh, no, gradient doesn't have an E in it. And it has an E, it's not the next letter. Gaussian error linear unit. Okay, cool. Okay. Sigmoid linear unit or swish function. I like it. Mm-hmm. Oops. Yeah. Okay. So this brings up a good point, right? So that activation function actually is not mostly going to be sigmoid. Hmm. Okay. Nope, nope, nope. Right, so that. They also do. Oh, okay. Also just call it the max of 0 and x. It works just fine. Alright, so sparse activation. So for example, in a randomly initialized network, only about 50% of hidden units are activated. Better gradient propagation, fewer vanishing gradient problems compared to sigmoidal activation, saturate in both directions. It's fair. Efficient computation, only comparison, addition, and multiplication, scale invariant. So max of 0, comma, a times x is equal to a times max of 0 to x. Makes sense. Right, it's literally linear for part of it. Potential problems, non-differentiable at 0, but differentiable anywhere else. Right. Fair. Not zero-centered, unbounded, and dying rectified linear unit neurons may sometimes be pushed into states where they become inactive for essentially all inputs. In this state, no gradients flow backward through the neuron, and so the neuron becomes stuck. Yeah. Slightly different form of the vanishing gradient problem. So, we've also got leaky gradient f of x is equal to x if x is a big number, and 0.01x if x is, well, less than negative number, less than 0. Okay, we can also just make it what's called parametric gradient. So 0.01 is just some a value. So pick a different parameter. As long as a is preferably small, that'll work out nicely. Alright, so this said, we can also do instead Gaussian. Gaussian error. Whoa. F of x is equal to x times Gaussian function at x, which is equal to x times the cumulative distribution function of x, whatever that might be. Right, CDF of the standard normal distribution. So that's kind of interesting. The CDF does look like CDF does look like a sigmoid, but you know, it's slightly different. Huh. I'd be kind of interested to know how that. I'd be interested to know if that does any better than the sigmoid, just because it is shaped the same. So I would think that it would have the same gradient problem. It's actually a thing. So sigmoid of beta x is going to get us this. That's equal to x divided by 1 plus e to the negative beta x. Beta is our trainable parameter. So it helps us change stuff as we start moving through this. That's interesting. Oops. Now I'm starting to wonder if I could go back and like fix all this stuff in my old programs. I'd also be interested to know what our I'd also be interested to know what our class would look like, if it's any different. Alright. I gotta train. Yes, I did just do that to myself. But oops. Oh, that's unfortunate. Wasn't paying attention, hit the edge of my computer. We'd have to write a research paper. That's just a pain. Not allowed to what? Write a research paper? Oh no, make a fully connected layer. I get the feeling like if you wanted to specifically or if you knew that like a certain layer would have 0 weight or something like that, then you should be able to make it sparse. But at the same time, like, how are you going to ensure that that happens, I guess? What do we get? Oh, lost it. Had a message pop up. Anyway, not important. So is it the... Is it essentially that, like, this thing just has too many connections? Evolution? Oh, I see. There was something somebody did recently. I just saw there was like a massive quanta. That one. Machine scientists distill the laws of physics from raw data. So this is a an article that was done in Quanta, where a couple of data scientists were like, we're gonna make this particular model and just like let the computer figure out what the parameters should be. And rather than doing like some sort of ridiculous thing like you're talking about where it's just billions of parameters, they were able to figure out like, here's some connections for making this work. I'm not entirely sure. I read this like 2 months ago also, so symbolic regression, that was it. Yep. well then. I'd say that's an improvement. Anyway. Anybody have any other mathy stuff you want to talk about? That's very interesting. Generates weight and run time for much smaller number of true parameters, so... I mean, I've got to go about remembering any of my programming at all. Oops. The correct website, if anyone's interested, is scilab.org, not scilab.io. Not sure exactly how that happened, but... Unless my version of Scilab is that old that it just had a dead link in it. Again, possible. So old. I had a student who was working on something for magic squares. She was trying to figure out squares of magic squares of squares, and trying to figure out if there was a way to create magic squares of squares, or to prove, as Ramanujan had tried, to prove that it was not possible. And she had some interesting techniques. I don't know exactly how close or far away any of this was, but I don't know. It was interesting. For part of it, she was kind of like repeating Ramanujan's original work on it, and then started deviating and going off on her own. And I'm like, this actually shows some promise, because she was trying to do saying like, oh, by the way, all of these squares mod 4, I guess, like have to have certain properties. And then if you can show that, then those same properties have to hold mod 8, mod 16, mod 32, and doing powers of 2 as you go up. Which kept like skimming off certain aspects of it and being like, okay, well, if it's mod, this mod 4, then when you do mod 8, like it's only a certain number of cases that we have to care about. The problem is you could have to do this indefinitely. Hmm. Are they computationally efficient? It's a decent question. Let's see. Okay. I'm gonna cycle water here for a second, and I will be right back. Gotta grab some more for my glass, and might as well run ads so it doesn't happen later, and we can disable pre-rolls for anybody else who's gonna be here. So, be right back. Give me a minute/2. Those bots know better. Well, yeah. And he breaks the rules. Yeah, so she was working off of the basic rules where you're not allowed to do you're not allowed to repeat the same number. It has to be magic square of squares, and you had to um, it has to be all of the things. Anyway, yeah, I'm gonna mess it up, but I might as well repeat some of it. I talked about this a really long time ago, so if you go back into the VODs, there's somewhere where I talked about it. I can't even tell you when it was. But yeah, she went through and said, all right, you got a squared, b squared, c squared, d squared, e squared, f squared, not that e, g squared, h squared, I squared, not that I either. Hmm. Would not surprise me. I guess I haven't seen the proof of that, but nonetheless. Alright, so if we like basically just focus on any one of the if we focus on any element anywhere in the entire thing, then we're going to say that, okay, a squared plus b squared plus c squared is going to be equal to a squared plus d squared plus g squared without loss of generality. This is going to mean that b squared plus c squared is going to be equal to d squared plus g squared. So anytime that you have any row and column that you're looking at, you're then going to be able to say, oh, well, based on this, I can then make our intersection just drop out. And then we end up with this stuff. Then we can shift stuff around and say, okay, if we want b squared minus d squared is equal to g squared minus c squared, again, without loss of generality, you can pick whichever ones you wanted. You end up with these things, which are now difference of squares. So since they're differences of squares, this is going to say that b plus d times b minus d is going to be equal to g squared minus c squared. Which means that g squared minus c squared needs to be divided by evenly either and b plus d and b minus d. So then what? Oh, man. Yeah, sure. If you can toss it out, we'll think about it and see what we can come up with. All right, I got it in my pictures here somewhere. Like I said, I posted this like super long time ago. She gave me a copy of her notes, which are also like scrawled in Arabic all over the place for little notes of hers, and I'm like, I do not understand what that means. I'm sorry. You could probably plug it into Google Translate. But nonetheless. Okay. So her thing was then, if you look at this and you say, Alright, g squared minus c squared mod 4. That's not what I wanted. That'll work. Right, I don't know if this is proper notation or not, but whatever, it's fine. So g squared minus c squared mod 4 has two options. We know for a fact that g squared minus c squared has to be in an integer because this is a magic square. Magic squares are all integers all over the place. That's all it ever is. So this is closed under the integers, and then the difference of squares mod 4 can only be one of two numbers. So if we had, let's say, we did this with all of the different combinations, where we said, okay, if you did C and G like this, and mod 4 they could either be 0, 1, 2, or 3. Oops, wait a minute. That doesn't work. Sorry, nope, hang on. Yes, 405 Jazz. Hello. Good morning. Hope you're having a lovely day. Go ahead and plug that into chat, and I will get to it very soon. Ugh. Oh, that's gross. The eraser could use some work. Right, so if we had just, again, without loss of generality, what do we have? This is 0, 1, 2, 3, and then mod 4, we've got c squared. Sinusoidal functions word problem. Absolutely. One of my specialties is trigonometry. I teach pre-calculus, mostly trigonometry, for most of my full-time job. So, all right. So if we have c mod 4, it can either be 0, 1, 2, or 3. Then c squared is going to be 0, 1, 4, or 9. And if we do this mod 4, this is 0, 1. 4 mod 4 is 0. And 9 mod 4 is 8 plus 1. So 1. So c squared can only ever be 0 or 1 mod 4. And likewise, g squared is going to be the same. So if we do c squared and g squared like this, 0, 1, 0, 1. You know what? I need a Punnett square. Man. G squared is 0, 1. Then what is g squared minus c squared mod 4? G squared is going to be 0 minus 0 is 0. 0 minus 1 is negative 1, which means that this is going to be 3 mod 4. 1 minus 0 is going to be 1, and 1 minus 1 is going to be 0. So those are the two options that we've got. Well, three options that we've got. G squared minus c squared can either be 0, 1, or 3 mod 4. And then there's a way to say, like, oh, by the way, if we have then b plus d, b minus d, there's a way to eliminate some of these options, then we can keep going with this over and over and over. So, let's hop on over to... Alright, two curves just real quick. Let me... Sum of 1 over n converges, choosing n as a fraction of n values from 1 to infinity. That fraction is a. So pick a share between 1 and 2, 3 and 4, 5 and 8, 9 and 16. Yep, 1732. Yep. Yes. So I have definitely seen in my Calc 2 class we did that as like 1 plus a half plus a third plus a fourth plus a fifth, etc. Ugh, I'm gonna have to write some of these. Right? So we're looking at values for 1/4. That's not what I meant. Values that add up to more than a half. So you've got a half or equal to. Here, 1/3 plus a quarter is greater than 1/2. 1/5, 1/6, 1/7, and 1/8 are all greater than 1/2. And you can go on from there and say that, okay, this is diverging. I'm going to have to come back to that in a minute in terms of the rest of it. Ferris wheel, it turns at a constant rate of 1 revolution every 4 minutes. The highest point of the wheel is 25 meters from, and the lowest point is 3 meters above the ground. Construct a graph that models a person's height on the Ferris wheel above the ground with respect to time. Yes. So what you're going to want to do is look at this in terms of, right, your height and time. You know that it starts where? So, like, where does a person have to start? Right, so at the bottom in this case, it's going to be 3 meters above the ground. So we know that, for instance, that's where the platform is. That's where, so not quite. The lowest point of the wheel is 3 meters above the ground because this is where, like, the platform is. Your Ferris wheel doesn't actually ever slam into the ground. One would hope. So this is where somebody boards the Ferris wheel. And when do they get back to that point? So how long does it take to get back to there? Right? So every 4 minutes, we could do this either as like 2 periods or 1 period, it doesn't really matter. So we know every 4 minutes, we're going to get back to the same spot. So after 4 minutes, we get back to 3 meters. And after 8 minutes, we get back to 3 meters. Okay, so if that's true, where else do you know, and when? Where else do you know on the wheel they're going to get to? Yep. So how long is it going to take for them to get to a certain other place on the wheel, and where is that? So you should be able to look at this and be like, okay, if it takes you 4 minutes to go all the way around, it's going to take you how long to get where else? Yep. So half the trip is going to be spent going all the way up to the top, and half the trip is going to be spent coming all the way back down because everybody else is moving at the same rate too. Right, so halfway here, you got 2, and that's going to get us up to 1, 2, 3, 4, 5, 6, 7, 8-ish, somewhere around here. I don't really know. It's not like it matters that much, but anyway. 2 minutes to get to the 25-meter mark. Which also means after 4, it's going to take us 2 more minutes to get to 6 minutes, which is going to also be at the top here, 25 meters. All right, where else? That's all right. No, that's fine. So you're doing a circle, right? We're going to be going in a circle, and we started at the bottom. And it doesn't actually matter which way we're going, so I'm just going to go like this. So this is 0 or 4 or 8, ... That's going to keep going out like that. Then the top here is going to be halfway in between all those. So this is going to be 2 or 6 or 10 and so on. Where else do we get on this Ferris wheel and when? If it takes us 2 minutes to get from the bottom all the way to the top, then it's going to take us right. So likewise on both directions, right? As we go up and as we go, sorry, other way. As we go up and as we go down. It's going to take us 2 minutes to get from the bottom to the top to the top to the bottom. Break it down further. So make a smaller segment. Where's a nice easy place to look at on a circle? If we've already defined these 2 points. Yep. So how do we figure out, first of all, when do we get there? And second, where are those? Or what are their heights? Now, their heights are going to be the same, right? Since it's both the sides, we're just going straight across. Sorry, straight across. There we go. Because you got the average height of the top and the bottom, which ends up getting us So 14 meters is going to be the midpoint, or the midline. This is where the spoke is in the Ferris wheel. So you've got the center, sorry, that's where the center is, where the spokes all go to. So you've got all these cross beams and things like that, which are connecting all the individual cars to the center of the, or to the Ferris wheel itself. All right, now I'm going to get rid of those because that's really distracting, but that's the idea. All right, when do you get to the sides? How long did it take? Yep, so it's all of the 1 minute segments that we have here that are going from the bottom or the top. It takes us a minute from either of those positions to move to the next, other way, to move to the next one. So those are to move to the sides. So from 2 minutes, it takes us 1 minute to get to this midline again. From 4, it takes us 1 minute to get there. From 6, it takes us 1 minute to get there, and so on and so forth. So these are always going to be here. And again, friends of the channel will know that this is exactly how I do graphing sinusoidal functions anyway. Start with the first and the last points on your period, and then go halfway. That's at the opposite section. And then go halfway in between each of those, and you get your midline. And if you're doing this right, you should also go halfway again, because it really helps you figure this out. Now, here's the thing. Halfway in between all of these sections along this is right here. What is the height of that location? Now, you don't need to figure it out in terms of, like, you know, exact numbers, at least not yet, but just look at it. Is it halfway between here and here? It makes it pretty obvious. Right? In terms of our angle, it's halfway. But if you just look at, like, the distance vertically versus horizontally, this is most definitely not halfway. So this actually ends up being, this is about half, this is about 3/4, and it's just slightly underneath that. So what I do, honestly, I don't even calculate what the number is, like 99% of the time, unless I actually need it. I'm going to go in here and I'm going to draw halfway in between 14 and 25, and then 3/4 between 14 and 25, and my point for here at 1.5 minutes is going to be just under that 3/4 mark. And again for 2.5 minutes. And again, back at 30 seconds. This is going to be, again, halfway, 3/4, and it'll be just above that particular value here. These are not linear. So if you ever see like it's drawing a straight line, don't do that. All right, these should not be straight. And then over here at, I already did 2.5. At 3.5 minutes, this is also going to be down here. At 4.5 minutes, that's also going to be here. 5.5 minutes, it's back up to the top. 6.5 minutes, up at the top. 7.5 minutes, it's back down here at the bottom. This gets you 9 points for every 1 period that you draw. This gets you a much nicer graph, and especially since you do not want these to be like a sawtooth graph where you just draw straight lines going between these, right? If I just draw a straight line, come on now. No, not going to do it. Of course. If I just draw a straight line going from one to the next, you see that this is going to miss those points if you draw them correctly. What this should look like is that this grows slowly and then starts curving up faster until we hit the midline, at which point it will start slowing down again and reaching that maximum. It's not going to be pretty first few times you draw it, definitely, but, you know, it'll be alright. But the way that sinusoidal functions are drawn in, you do the same deal every time. Everything above the midline is going to be concave down, and everything below the midline here is going to be concave up. Everything. And if you messed up your drawing, you just redo part of it. It's fine. And for you, you're going to want to label those points, at least the obvious ones, right? The top, the bottom, and the two sides for all of these. These are going to be all of these points. You want to label these with their coordinates. Now, if you want the equation for this, this is actually pretty easy. We can make all this work. So, again, I do this all the time. The height as a function of t, it's going to be equal to. We got a times. Now, you can decide which kind of function you want to use here, either a sine or a cosine, but it should be pretty obvious in this particular case. We have a minimum value, so we want that to be a cosine, right? The minimum value is on t equals 0. So let's have this be a cosine. That way we don't have to shift this left and right at all. All right, cosine of b times quantity t minus c plus d at the end. A represents the amplitude. So the amplitude of this wave is the distance from the midline to the top or the midline to the bottom. Take your pick. Right, because it's literally the same thing. If it's not, you got a problem. No. So, A is going to be that. The period ends up being from when we get from one trough to the next, or one peak to the next, or from one place on the midline to another place on the midline that is going in the same direction. So here we don't go this one, because that's only half a period. It's going down instead of up. We want this to be going from where it's going up to where it's going up. So from here to there, or from trough to trough, or from peak to peak. Take your pick. In that case, right, our tau, the period, is going to be 4 minutes. All right, A was from 3 to 14 is 11 meters. Now here's the thing. Tau and the B value are related to each other. So B is equal to really. B is equal to 2 pi, which is the default period for a cosine function or a sine function. So 2 pi divided by tau. Which is going to be 2 pi divided by 4. So we want pi over 2 as our B value. All right, D is the midline. So like y equals 14 is the midline, it is D. The default midline is at 0. So it's all shifted up by 14 spaces in this case. Okay, so D is 14, and C is the phase shift. So, and I have to be careful here. It's not technically the phase shift. Phase shift is how much, what is it? How many periods this thing has been moved over. So that doesn't exactly exist in this particular case in this formulation. What happens is when you multiply out B times C, that's your phase shift. So it's like the number of periods you're moving. That's not entirely correct. Anyway, it doesn't really matter. I try not to use it as much as possible because, again, phase shift is not the correct term for it in this form. But putting it all together, this means that h of t is going to be equal to A was our 11 meters times the cosine of B is pi over 2 multiplied by, well, in this case, t, but minus 0, so it's just pi over 2t. Plus 14. In addition, if we want this to be a sine function instead, then we just alter this and say, okay, this is going to be h of t is equal to 11 sine of pi over 2 times the quantity t minus. In this case, we want to know where do we shift the origin point. The origin point is that one right there. Because for a sine function, a standard sine function, oh, you know what? I missed something. I'll get it in a sec. For a standard sine function, we have when our function goes up like this, it's the 0, or where do we hit the midline? And here, that's at 1. So it's going to be t minus 1. And then plus 14 on the outside. All right, so that's how you get your sine function if you want to do that one. The cosine, I forgot completely. Usually you start at the maximum. So in this particular case, this is going to be a negative because we're starting at the minimum, and then we're going up from there. Alrighty. How are y'all doing? Yep. Yep, no problem. And thank you for the follow. I mean, I had them do most of the work. In terms of reasoning where things were. That's the other thing, two curves, is that like you notice what I did throughout most of it, right? It wasn't here's how you do this. It was how do you get this? And where's that going to be? And let's show the proper way to think about things instead of like here's an answer. So I don't feel bad when I'm like, giving away answers, but it's because I'm making the student do most of the work anyway. Like the only part that I had like really done myself is the getting the quarter points up here, right? Oh yeah, I know. I walk a very fine line. Yeah, I walk a very fine line because I know that like I'm the one who's teaching this, and so like I know the questions that need to be asked in order to make sure that the student really at least kind of understands it for the next 2 minutes anyway. But yeah, to get these quarter points, like I mean, I guess we could go, this is going to be 14 plus or minus square root of 2 times a 11 over 2. Root 2 over 2. Yep. There you go. There's the numerical values for you. But, I mean, realistically, what do we do here? I draw in the half and the 3/4 marks and then go slightly underneath that or slightly above that, depending on which section we're in, and just say, good enough. Hmm. Okay, so she broke this down into a bunch of different parts here. I'm not sure we actually have to. I think I can generalize and say, like, alright, well, this is similar enough that, like, these particular cases... That was part of what I had to say to her when she did this, was like, you're duplicating a bunch of cases, just whittle them down. Okay, so then here, this is when g squared minus c squared is even. These two are when g squared minus c squared is odd. So then b squared minus d squared must be the same. B squared minus D squared has to have the same parity, which means that and B squared minus D squared mod 4 must be the same as G squared minus C squared mod 4. So then our possibilities for this are either that B and D, okay, alright, so B squared minus D squared has to have the same parity as G squared minus C squared. And they have to have the same value mod 4, and they'll have to have the same value mod 8, mod 16, mod 32, etc. Now, in theory, you could also do this in terms of, like, other numbers, like, you know, mod 5 or something, but the point is that doing this with mod powers of 2 is a lot easier, because you can end up saying, well, what is this thing going to look like if, you know, if any of these numbers are even, then we can turn it into something that's, you know, 2k, where k is an integer. If it's odd, then it's going to be 2k plus 1, which is an odd number, as long as k is an integer. So B is going to be equivalent to D mods 2, 4, 8, etc. Or if they're opposite, if B and D have the opposite parity, then it only works in one way, so these have to match. Then hang on, I'm not looking at the right one. Yeah, this boils down to parity. I was looking at this one. This ends up being B squared and D squared. Have to have the same values. going nuts. Yeah, okay. So b squared and d squared have to have the same parity here. Or b squared and d squared have opposite parity, in which case b squared and d squared have the same parity, then c and d also have the same parity. Right, that implies four. Hang on. Friggin' A. Alright, let's do this one at a time. So if we do it with 2, that's going to mean that B and D have the same parity. Mod 2. Alright, and if B squared and D squared have opposite parity, then alright, anyway. Spells came on. So, that means that B and G are going to have the same, that means that they're going to have, yeah, they have to have the same parity. They have to have the same value that we get out of this. So, B and G have to be the same, and then therefore, right, D and C. D squared, C squared have to be the same. Because if they're opposite, they end up getting different numbers back. We end up with the 1 and the 3, because when we do it mod 4, they end up switching. Right, it was a -1 mod 4, so 3 mod 4. Okay. So then these are the only possibilities that could possibly exist. Ugh. Which then, if B squared, G squared have to be the exact same thing here, this means that, like, the 1 here means that G squared was 1. So then, therefore, G had to have been either 1 or 3. Mod. 1 or 3. Really? mod 4. Whereas these two, D and C, would have to have been, what, 0 and 2, right? Yeah, we need to get our 0 for C squared. So 0 for C squared gets us 0 or 2 mod 4. B, right? B and G for the first one here. And here, C and D would have to be equivalent to 0 and 2 mod 4. Right, and that's an AND. So both of those things have to be true at the same time. Or these could be switched for the other one. So this is a big OR here for these two statements. B and G could be equivalent to 0 and 2 mod 4. And C and D can be equivalent to 1 and 3, 1 or 3 mod 4. So then there was something else that was happening here. That may be as many as I can eliminate. Majestic, thank you very much for the follow. My name is Obi-Wan Pez, this is N-Simplex Pachinko, and we are doing some math this morning. My usual streaming nights are Wednesday and Friday, US East at 9 p.m. To give you context, I will likely be streaming again in 8.5 hours. However, my Wednesday nights are usually math, my Friday nights are usually gaming. So, hello. If you have any math questions, let me know, and I will get to it fairly shortly. Oh, no, never mind. That was incorrect. I didn't need that. This was a big OR between these. Today is Friday, yes. So I'm streaming math because I didn't do it on Wednesday. You don't. It's all right. Yeah. No, that's fine. I got you. 2745. So this is making a. You're saying it's a three-dimensional pyramid? I do, but my Discord is currently still personal, so I'm leaving it closed for the moment. Eventually, I might open one up. But for now, I've also been over on who's it's the math. What are they called? Yeah, homework help. So I've been hanging out on homework help a lot, and oh well, thank you. And as I showed you, I'm pretty decently willing to help, but at the same time, gonna make you work for it. So. Okay. Oops. That's good enough. Two sides. Is this the picture we've got, or is it more like a triangle? Or kite, for that matter. Kind of like this. Okay. So if I label ABCD like that, I do also have another streamer who will do math quite a bit. Scrap everything. Okay. Replace A for C. Replace B for A. And C for B. Cool. So his name is Megalomorph. He does occasional math streaming and does other sorts of really cool stuff. Mostly talks about like high-level type math, but is willing to help out in any way that people need. So Megalomorph is also a bunch of fun and enjoys the dad jokes about as much as I do. So it's all right. I do have to say that this is going to be the last one. So we're gonna head out of here pretty soon, but I will raid on to somebody else and see if there's anybody in science math. Category. Nope, we're the only ones. Cool. Science and tech. Sorry. Live B cam. I think I'll pass on that one, no offense. Okay, one more time. A to B is 6.2. A to C is 8.5. Angle A is going to be 27 degrees. And CBD and BCD. That angle and that angle are going to be the same, which is 45. Come on. All right, so quick way. First off is you've got two angles which are going to be 45 degrees. This is going to tell us that this side here, opposite this 45-degree angle, is going to be the same as this side here off of this, opposite this 45-degree angle. In addition, because you know the three angles of the triangle, or you know two of them, now you can find the third. So this is going to be a 45, 45, 90 triangle. All right, with that, we don't have any of those measurements, which is going to be interesting. Got a 45, 45, 90 triangle. D, B, C with a 27-degree angle over here somewhere. Equal to each other. This is 8.5. Ah. The other question, are D, B, and A collinear? Are they in a straight line? Because if DBA is a straight line, then this makes it a lot easier. I'm guessing yes. Yes. Okay. Yep. Well, have a nice day, 405 Jess. See you later. No problem. I would say that if this is collinear, yep, then what you can do is stick an X here for this length here, which is going to be the X is that length there. Now you should be able to create a Pythagorean triangle using your large one. And you only have one term, x squared, or, well, x, that you're going to have in for this. So here, you can use this as, this side is 6.2 plus x, parentheses squared, plus 8.5, oops, nope, ew, vertical x squared is going to be equal to hypotenuse, 8.5 squared. All right, go from there. Should be able to get that, no problem. Okay.